In this clip, we're going to be looking at transformation of functions. All the way through my explanation, I'm going to be using just one function, and that's this equation here, which produces this graph. There are 4 different transformations that we're going to be looking at. The first one is translating the graph up and down. The second one is translating the graph right and left. The third one is reflecting the graph in the y-axis. And the fourth one is reflecting the graph in the x-axis. Let's begin our journey into transformation of functions by looking at what happens when we add something onto the end of our function. For example, let's add something onto the end of this function. Let's just use 1 to start with. So here's my equation, and I've added on 1. What effect do you think this will have on the graph? It moves up by 1, and that's because all of the y values have increased by 1. If we add 2 onto the function, the graph moves up by 2. Adding 3 moves the graph up by 3. Now what would happen if a is negative? In other words, we take something away from the function. If we subtract 1, you'll notice that the graph goes down by 1. If we subtract 2, it moves down by 2. And if we subtract 3, it moves down by 3. So when we add a onto a function, we can say that we have a translation by the vector 0a. A can be either positive or negative. And remember that when we have a vector like this, the top number tells us how far we move left and right, and the bottom number tells us how far we move up and down. Here's a question for you to try. Press pause and have a go. When you're ready for the answers, press play. To start question A, I found a convenient point on the original graph. I'm going to choose this point here. I can see that on the red graph, it's here and it's gone up by 3. So 3 must have been added on to the equation, and you can see that here. Now the question doesn't ask for the equation in its simplest form, so this would actually be accepted. But I always like to tidy things up a bit. I can see I've got +1 + 3, so that's actually +4. So this is a neater version of my final answer. We've already said that the graph goes up by 3, so it's a translation by the vector 0, 3. The next thing that we're going to look at is adding something onto the value of x and then performing the function on it. Let's look at what happens to this equation when we add 1 onto the value of x each time. So you can see everywhere I've got an x here, I've got x plus 1. So I've got x plus 1 cubed, that's that bit. X has turned into x plus 1 here, I've got 3 of those squared, and I've still got the +4 on the end. What effect do you think this will have on the graph? Now 99.9% of all known people automatically think that this graph will move 1 to the right. But it actually moves 1 to the left. Let me try to explain to you why this happens. Let's take a value for x. Let's choose 1 for the first one. So we would have 1 here and 1 here. Now, because we've got 1 + 1 here and 1 + 1 here, this equation will actually return the value for 2, because we'll have 2 cubed minus 3 times 2 squared plus 4. So when I'm at 1, I will actually get the value for 2. If I now take another value for x, I'm going to choose -1 this time. Watch what happens. I've got -1 + 1, so I'm actually going to get 0 cubed minus 3 times 0 squared plus 4. So -1 is going to return the value for 0. So the -1 here will return this part of the graph here. So as you can see, every value is moving 1 to the left. And the graph should look something like this. Now, what do you think will happen if instead of adding 1 to x, I add 2? It will move 2 to the left. Now, what will happen if a is negative? In other words, we subtract something from x before performing the function on it. If we subtract 1, the graph moves 1 to the right. Subtracting 2 moves the graph 2 to the right. And subtracting 3 moves the graph 3 to the right. So to summarise, if I add something to x, then the graph moves to the left. And if I subtract something from x, then the graph moves to the right. It's important to remember that this one goes the opposite way to the way you think it's going to move. We can say it's a translation by the vector minus a, 0. Remember, this tells you left or right, and this tells you up or down. Here's a question for you to try. Press pause and have a go at it. When you're ready for the answers, press play. Here are the answers. To get my answer, I looked at the graph here and chose 2 convenient points. I then looked where they'd moved to on the red graph, and I could see that they've both gone 4 to the right. Remembering that it's the opposite to what you always think, this means we must have minus 4. Notice that here I haven't expanded the brackets at all. This is a perfectly acceptable answer, and you should leave your answer in this form. When we write the transformation as a description, it's a translation, and it's gone right 4, and then it hasn't moved up or down, so this is our vector. Here's another question for you. Press pause and have a go. When you're ready for the answers, press play. Here are the answers. For part A, if the graph of x squared has been transformed by 0 to 2, then that means it will have gone up 2. So we add 2 onto the end of the equation and get x squared plus 2. For part B, adding 1 onto the x before performing the function on it means that the graph will move 1 to the left. This is just a sketch, so we move the graph to the left and then mark that the bottom will be minus 1. Here's another question for you. If you look carefully at the graph, you'll notice that it's moved horizontally and vertically this time. Press pause and have a go. When you're ready, press play. Here are the answers. This time, if we choose points on the black graph, we can see that they've moved 3 to the left and then 2 up. Again here, 3 to the left and then 2 up. So the movement of 3 to the left means that we must have added 3 onto the x, and the movement of 2 up means that we must have added 2 onto the end of the whole equation. If you've left your answer like this, it's perfectly acceptable, but I've done a slightly tidier version here. This movement, 3 to the left and 2 up, can be represented by this translation vector, minus 3 for 3 to the left and 2 for 2 up. Here's another question for you to try. When it asks you to show clearly the coordinates of the vertex of the graph, it's talking about the turning point, so the vertex of this graph is this point here. Press pause and have a go. When you're ready, press play. Here's the answer. We're now going to look at reflecting a graph. So let's look at what happens if we put a negative sign in front of the function for x. In this instance, we get this. What effect do you think this will have on the graph? It reflects the graph in the x-axis, and this is because all the values of y change sign. So if they were positive, they become negative, and if they were negative, they become positive. If we're asked to describe the effects of this, we can just say it's a reflection in the x-axis. Here's a question for you. Press pause and have a go. When you're ready, press play. Here's the answer. We can see that the graph has been reflected in the x-axis, so it must have a negative in front of the function. So this is our answer. Now we're going to look at what happens if we put a negative sign in front of x before performing the function on it. So for this equation, we get this. What effect is this going to have on the graph? It reflects it in the y-axis. If we're asked to describe this effect, we simply write reflection in the y-axis. Here's a question for you to try. Press pause and have a go. When you're ready, press play. Here's the answer. This is telling me that the graph is reflected in the y-axis. I've done a sketch of that here to help me visualize where the minimum point will be. But you don't have to do a sketch, you might find that you're able to do it without one. So here's a summary of the 4 transformations that we've looked at in this clip. If we add something onto the end of the function, then the graph moves up or down. If we do something to the x, then it moves left or right. It's the opposite to what you think, so if we add something it moves left, and if we subtract something it moves right. This is the one where more mistakes are made than any of the others. If we put a negative sign in front of the whole function, then the graph reflects in the x-axis. If we put a negative sign in front of the x before performing the function on it, then the graph reflects in the y-axis. Here's a set of questions which uses everything that we've learnt in this clip. Press pause and have a go. When you're ready, press play. Here are the answers. For this one, the graph moves 5 to the right, so I've added 5 onto the x-coordinate. For this one, the graph moves 6 up, so I've added 6 onto the y-coordinate. For this one, the graph reflects in the x-axis, so I've made the y-coordinate the negative of what it originally was. And for this one, the graph reflects in the y-axis, so I've made the x-coordinate the negative of what it originally was. To finish, here's a challenging question for you to try. Press pause and have a go. When you're ready, press play. Here's the answer. To get this, I noticed that first of all, this graph needs to be reflected in the x-axis to turn it the right way up for this one, and then it needs to be moved up by 3. So the reflection in the x-axis means that I put a minus in front of the function, and then to move it up by 3, I add 3 onto the end.